So I'm excited to be here today to talk about how AI will be everywhere and how to democratize artificial intelligence with an open platform and an end-to-end ecosystem. I think it's important that this is a technology that's available to everybody. That's what's making it so exciting to be working for Huawei. They've brought communications to every corner of the planet, and this is an exciting opportunity to do the same for AI. So when we talk about artificial intelligence, we talk about applications that can do specific human-like tasks, like classify real-world data, recognize objects, understand language. And that is usually done with machine learning techniques. To do that, we automate model build to iteratively learn from data. So in a sense, it's programming with data and find insights that would escape programmers or would be exceedingly difficult to capture with traditional programming methods. And we rely on self-learning. We want these systems to be able to adapt when new data is received and to update models based on data that are observed in the field. The advent of AI has been predicted before, but this time it's happening. And one of the reasons why it's happening is because there's an urgent need. With the advent of big data, with the availability of very large data sets, with the internet, there is an economic need. It's practically impossible to process the data being generated today, even before wholesale Internet of Things implementation, where we expect eventually to have sensors everywhere. It's practically impossible to rely on humans to understand and classify and process those data. For that, we need to rely on machine learning techniques, and in particular, deep learning. And so that's propelling AI forward. That's creating the need and an economic motive. And so with that, we're seeing that strides are being made in AI that were unthinkable just a few years ago. The time is right to implement AI systems for a number of reasons. First, we finally have systems that provide enough computing capacity to build high-quality models. One thing that we had been lacking in the past is the sheer compute capacity to train complex neural networks, to build models of the real world, to extract features from large data sets. With the advent of accelerators, with the advent of very large systems, that has changed. And so finally, we can build systems that have more neurons than a fruit fly, and that has beneficial effects. Those networks can be more intelligent than a fruit fly, too. So that we're able to build deep neural networks, and we have many flops, many floating point operations per second that we can execute, which means that we can train these networks and use deep learning as a way to automate feature extraction, to capture the features in data without human intervention. Finally, for every technology, there's always this one moment or several moments where a event sort of attracts the attention to the field and brings new ideas, brings new participants to the field. That, for neural networks, has been the ImageNet competition, which was won in 2012 by an algorithm called Supervision. It was a neural network participant in a computer vision competition that had been held for many years. And it won the competition. Not only did it win the competition, but it won it by such an impressive margin, 10%, that equaled the rate of traditional computer vision improvements in a decade. That just was an attention getter and has brought new interest to the field, has brought new practitioners to this field, has expanded the use of neural networks dramatically, finding new applications, finding new ideas to use this technology to build AI systems. Since that initial competition win, the ImageNet competition has been won by a neural network-based AI algorithm every year. And there's been a 5x improvement of the error rate in just a few years. Again, a dramatic improvement. The neural network-based image classification systems are now more accurate than humans. And if you look there, it's becoming, going under 5% error rate. Very impressive and many advances. So why machine learning and deep learning? Today, if you wanted to, machine learning and deep learning is a way for systems to do what humans can do without even thinking about it. And if you ask a programmer to develop an algorithm to recognize a bicycle, that's easy. All you need to look for is two wheels and pedals and the saddle and handlebars, right? Well, this is a bicycle too. So you show that to the programmer, he'll update his model, add some more rules, and you'll recognize this. Well, what about this? Yeah, the model was written, the wheels need to be on the bottom. Well, okay, update the model again. And hey, this is sort of a bicycle too. I guess the rule with two wheels isn't really a strict rule, so let's update. And you can keep doing this. We'll recognize all of these as bicycles. Yeah, a trivial rule-based computer system, not so much. The point is, recognizing real-world situations with rule-based systems requires a lot of rules, a lot of fuzzy rules, and there are not enough programmers in the world to write all those rules using traditional programming techniques. So that's where machine learning, deep learning techniques come in. They can automate that rule creation from data sets. And this is accomplished using neural networks, which some people claim are based on how the human brain works. I'll say that's a bit preposterous. We still don't quite know how the human brain works. I'll call it inspired. That is, it's trying to replicate some features of the human brain that we do know about. Specifically, having lots of small compute engines called neurons that take inputs from either data or other neurons. And those neurons are organized in layers. And then all you have to do is train them, right? Well, there are lots of ways to train them. And we'll hear a lot about different techniques and how to use those networks in the rest of the conference. So I'll leave it at that. Looking at the performance, looking at how quickly neural networks have scaled up in terms of capacity and performance, we see a performance growth of 2x, a doubling of performance every 3.5 months. That's outstripping the old Moore's law, which at one point was doubling of compute capacity every 18 months, and then we relaxed it and said every 3 years. Here we have a doubling every 3.5 3 to 5 months, or if we look back over the last 6 years, in 6 years, the compute capacity needed to train these neural networks has grown by a factor of 300,000. So that captures the growth, the capacity that captures the new capabilities these networks offer, and ultimately the ingenuity and the new ideas being created around this technology. So very exciting and a good time to be working on AI. What's behind these improvements? Well, on the one hand, algorithmic innovation. Innovations in neural network architecture are creating new capabilities, are creating new ways of using neural networks. And there are improvements in training algorithms to train those neural networks more efficiently, more effectively. Also, we're seeing the training data being more sophisticated. There's a renewed emphasis on collecting training data that is used to train those neural networks. There's improved collection and pre-processing of these data. And we're seeing increasingly larger training corpora, which is ultimately where the network gets its intelligence from the training data itself. And thirdly, we see a ever-increasing compute capacity available to train those neural networks with these large data sets. And that, in turn, enables us to make use of these large training corpora and train those ever more sophisticated neural networks to accomplish new things. We're clearly outstripping Moore's law, which is running out of steam anyway. Largely due to limitations in device physics, the size of transistors has become so small that it's nigh impossible to scale down transistor sizes much more. And the improvement in performance is no longer there that we used to take for granted for many years. So how are we delivering these performance improvements that are necessary to train these more sophisticated neural networks, to power those neural networks and other AI algorithms? On the one hand, with architectural innovation, we find that with application-optimized accelerators, we can get more efficiency from the network, the circuit technologies, from the silicon that powers our systems, and also with hardware-software co-optimization. By optimizing the hardware and software together, by integrating them more closely, we're able to get improved performance and a better ease of use. And so we can continue to scale up the performance. We can build more sophisticated networks and continue growing the systems that way. There's now been basically 3 generations of accelerated AI systems developed over the last couple of years. It all started out with a basic system and a single accelerator. So the idea behind these compute accelerators is that rather than providing the full flexibility of a traditional CPU, of a traditional processor, you have a very optimized piece of silicon that is very good at just one type of processing, number crunching, as it's used for the training of neural networks. So we all started out, pretty much every company, every practitioner in AI, started out with systems that had one of these accelerators, typically in a slot in a PC or a server. And then that proved not good enough anymore. So in the second generation of systems, we went to multi-accelerator architectures, where one system was paired with multiple of these accelerators. You see the accelerator box that attaches to the system is now larger than the system, the computer system itself. And more recently, most companies in the field have started to use clustered solutions where we take those basic building blocks of a multi-accelerator system and we combine many of these together with high-speed networking and create very large cluster systems to train ever more sophisticated neural networks. So that's the state of the art. A dramatic improvement in performance in just a few years. It took many hours, in fact, many days with the original technology to train the AlexNet algorithm, the first winner in that, the first neural network-based winner in that computer vision competition. By now, the most sophisticated neural networks that can perform the same task, classify images from the ImageNet data corpus, can be trained in under an hour using these clustered accelerators. So very impressive with the arrival of these clustered accelerators, and that's really where research becomes practical to try out new architectures, to innovate, and to drive forward the technology. So key ingredient here, these large capacity training clusters. All right, now let's look at the real world. The real world is driven by big data. The world is big data, if you think about it. So and that's why these large clusters are really important. So if we look at the ImageNet corpus, it has 40 million images and reasonable resolution. That makes 2.8 trillion pixels in the entire ImageNet database. When you talk to a cancer researcher who's looking at scanned oncology slides, they'll point out that those 2.8 trillion pixels, that's 474 biopsy slides from patients. That's not big data to them. They're getting 40,000 of these slides per month. So we're talking about real need here that's dwarfing the ImageNet that used to be considered big data. And so there is a demand for this sort of compute capacity and to be able to process these quantities of data. It's now over a petabyte of compressed image data just at Memorial Sloan Kettering and counting. And so it's critical to keep developing and pushing the boundaries on the technology to provide these new capabilities for next generation systems to have real world impact in medical research, in civil engineering research, in many applications that affect the lives of everybody. So the title of my talk was AI Everywhere. And so if you look around, AI implementations are now seen across the field, from the cell phone to assisted driving technologies and eventually self-driving cars, in your computer, in security cameras, in medical research, in medical diagnosis, and in the cloud. So you can classify that in AI being done for you on your behalf and by you in your cell phone, in your car, on your system. It's critical to have end-to-end interoperability between all of these systems. Why? On the one hand, as new research becomes available, We wanted to benefit all of these application areas. We also want to make sure that developers that have the experience in delivering new applications are able to apply them to different systems, and so make the best use possible of that scarce resource that's human ingenuity. AI also stands for autonomous intelligence. So many of the systems that we have where we're building AI, we need them to work even when they're not connected to the network, even when they can't rely on computing resources that are at the other end of a network, whether it's in the cloud, whether it's in a proprietary data center owned by a company. We want those systems to have sustainable operation, disconnected operation, and real-time response. It's, why is that important? On the one hand, being able to process data on your mobile device when it's disconnected gives more capability to that device. You might not always be able to get a network connection, but you still want to use your device to either translate or help classify, for example, medical data. If you're a doctor seeing a patient somewhere where there is no network connection. I spent a summer several years ago in Senegal looking at e-medicine in Africa, and it's exciting what you can do with this technology. But in many of these offices, you can't always rely on having a network up and running, yet you still want to be able to use your device to do diagnosis. Also, being able to process data on the device is much more energy efficient. Sending data over a network requires a high-powered radio to be activated on the cell phone. That uses a lot of power. There is also the possibility that you have network congestion, that you can't get to the server. And in all of these situations, you still want to use your cell phone. It's even more obvious why you need disconnected operation for technologies like self-driving car. When you lose network connectivity, you don't want the car to hit the wall or be forced to stop. It's critical to have fail-safe, independent operation regardless of network, and ultimately to have real-time response. If there is a network delay, if there is a problem with the network, you still need a assisted driving technology to warn you if you're about to hit another car. You still want security cameras to recognize dangerous situations and so forth. So that gives us two ways to deploy models, either on an endpoint device such as on a cell phone or in the data center, and access the capabilities over the network. And both have their use cases. At the cell phone level, we are finding that accelerators are useful much in the same way that accelerators for training help in propelling the advances, making neural networks smarter by providing more capabilities to train them. We can have more power-efficient processing of ever more sophisticated networks on mobile devices using NPUs, neural processing units, special processor types that have been optimized to handle neural networks. The first such cell phone on the market was introduced by Huawei last year. It's based on the Kirin 970 mobile platform. And so that platform has NPU built into the chip that is in every cell phone. with that new chipset. It has an API, a library that can be used by neural network developers to build applications and evaluate their AI algorithms with this accelerator. And then the mobile operating system assigns the tasks to the different purpose-optimized processing units like the CPU, the GPU, or now the NPU, the neural processing unit. That makes processing both much faster and more energy efficient. It makes it feasible to do much more processing on a mobile device in a disconnected manner. So with that, you get an environment where you acquire data on a mobile phone. It's amazing the amount of data that, and the different types of data that you can collect with a mobile phone today, and evaluate those data directly on the network, on the device itself. Of course, you might still want to upload the data to analyze a larger data set, for example, captured by different users. You can store the data and use it to train an updated network model that you can then deploy to the mobile devices to improve the model quality and handle new data, new types of application needs as they're discovered in the real world. An alternative to the in-device use is the in-the-cloud use of neural networks. In that scenario, you upload the data gathered on the device. The processing is done in the cloud, and you get the results back on the mobile device. That makes sense for processing needs that are much larger than is possible by a mobile device and the power available on a mobile device. And then, again, you can store the data and use it to train and update models and deploy updated, enhanced models at a later time. Of course, the right answer may be a mix of both of these models, where for many data, for many situations, you can analyze the conditions on the device, and then, like we do in the real world, when you have a tough problem, you call mom, and you send the data back to the cloud. You have more processing capability there, and you can augment what can be done in the device. Again, you compare that with updating the model and deploying enhanced models into both the cloud and the mobile devices. Right. So I think it's fair to say that just judging from the amount of AI implementations that we're seeing, we're entering an era of AI where AI is being built into all types of new devices, and where AI is really starting to define and become a new era of computing, much like previous technologies that have marked their own era by creating new ways of processing and handling data. If we look back, the PC era was the first time that end users were able to process and store data with computer technology. The internet era enabled us to find and share data with others. And with the AI era, we're hopefully finally able to understand large data sets and discover information in them. So this is paired with many other technologies that create more and more data, mobile devices on the one hand, the Internet of Things on the other hand, where we find more and more sensors, where we embed sensors and intelligence, the ability to gather ambient information in many objects of everyday use, and we can feed them to AI algorithms to make sense of the data being observed. There are many more breakthroughs to come. One that was fairly recent was actually started here in the city of London at Google's DeepMind lab. For many years, Go had been held out as that one game that is so sophisticated that computers may never be able to beat a human. While the AlphaGo program developed here by Google's DeepMind lab accomplished that in 2015. The first implementation, AlphaGo, was based on AI learning from past games. So there was a vast library of previous Go games that humans had played, and the neural network trained on that. So some naysayers said, well, that's not real intelligence. All the AI algorithm did is basically memorize and find smart ways to apply human moves that humans developed. So AlphaGo Zero was the next technology developed by that team, which was AI training to play Go without access to a human library. And in fact, it turns out that AlphaGo Zero trained more quickly than relying on human games, a library of human games, a history of Go games that humans had played. All that algorithm had was the rules of the game, and it was able to play itself. So in a short term, it surpassed human capacity. And to bring the technology full circle, the newest variant of that is AlphaGo Teach, where the AI algorithm can now teach humans how to become better Go players. So again, amazing progress in just the last few years on what had been considered one of the really tough challenges in AI. And I think many more breakthroughs are still to come. I'll warn that the naysayers will soon be in the airwaves again and point out that AI isn't really delivering on the promise. That largely depends or is based on an observation that's also known as Tesla's theorem, which can be encapsulated as AI is whatever hasn't been done yet. So every time we accomplish something that is considered really tough and computers will never do it, we redefine that. That's not really tough. That's just some computation. Well, by definition, everything a computer does is computation. So I mean that. So for many, many years, chess was held out as this paragon of human intelligence that a computer will never be able to do. And Deep Blue beat Kasparov. And so then the naysayers changed tone and said, just a game, who cares about that? Understanding questions and answering them with witty remarks is what human intelligence is really about. Like the game Jeopardy, which runs on American TV. I'm not sure if that really is intelligence if you've ever seen the game, but challenge accepted, and IBM built the system, and they won against the undisputed champions of Jeopardy. And so, again, some people will say, "Oh, it's just a game show. Who cares about that?" Understanding, real-world scenarios. Well, ImageNet is now good. Neural networks have become better than humans at classifying pictures. Again, whatever it is, surely that's just computation, and we'll find a new challenge. But that's also good. We should look for these challenges, and we should find ways to solve them. I just don't want to leave you with that impression, when the newspapers start getting tired about running the stories of how remarkable AI is, they will surely turn and start the other set of stories, how, what a horrible disappointment AI has become. at that point, everything that was accomplished will just be normal computation, and they'll find a new challenge. And that, again, that's good. We need challenges. That's a way to push the boundaries. It's a way to train new generations of scientists to develop new ideas, and something that we come to conferences like this to talk about new ideas to solve new challenges. So I'm looking forward to your ideas in this, and let's keep pushing the boundaries. So I want to conclude that AI is starting to be implemented everywhere. What we need to do is democratize the technology, make sure it's available everywhere to everybody, and that it's open, that it's resilient and sustainable, and it's accessible from a range of devices, so that wherever we need that new computing technology, we can take advantage of it. I'll conclude at this point, and we'll be happy to take your questions. Thanks.
Thank you so much, Mr. Gschwind.